Welcome to STEMKits from iBio Institute. Do you know what solubility is? Today, we will be exploring the solubility of different chemicals and investigating how fast chemicals can dissolve. When you have some ideas about solubility, you will be a chemical engineer as you design and build a time-released medication tablet. My name is Grace, and along with the rest of our STEMKit team, I will be guiding you through this investigation and engineering challenge. We can't wait to see what you do, so let's get started. Doing an investigation scientifically is different from just playing around. Chemical engineers investigate chemical processes in a very deliberate way. They are careful to set up experiments by changing only one variable, while every other factor is held as constant as possible. First, we will explore solubility by changing one variable, the solvent, to discover how it affects the solute. In the second experiment, we will change the form of our solute for its effect on solubility. Your final challenge is to engineer a time-release medication tablet. Engineering is a form of practical applied science. Like all scientists, engineers test out their designs and change the design when it best suits their needs. They always write their design choices on their design documents so that they can remember their alterations. You have charts and design plans in your STEMKit instructions that you can use and then tape into your Young Scientist journal as a record of your work. Don't be afraid to test your ideas, and don't forget to write them down. Before we tackle our engineering challenge, we will need to know something about solubility. You see solubility every day. Solubility is the word we use to describe when a substance called a solute dissolves in another substance called a solvent. This happens when we mix sugar with water. The sugar dissolves in the water. This means that the sugar is soluble. Why does this happen? A solvent is usually a liquid, like water or alcohol or oil. Solvents are made of molecules. Some solvent molecules, like water, have positive and negative charges on them, like you can see in the diagram. A solute is also made of molecules. Some solute molecules have positive and negative charges on them too. Positive charges are attracted to negative charges, so when we put them together, the charges on the solvent will pull on the charges on the solute. This drags the solute molecules away from one another and hides them in the solvent. The solute is soluble and dissolves in the solvent. Because each solute and solvent have different charges on their molecules, each solute dissolves differently in different solvents. The rate of solubility can be changed by the form of the solute. The solute can be packed together very tightly, or a coating of a different molecule can be put around the outside of the solute to delay the start of dissolving. The solute can be loosely packed, or even be a powder which is not packed at all. Which form do you think will dissolve fastest? Which will be the slowest? Food scientists and pharmaceutical scientists have learned how to control the speed at which a solute dissolves into a solvent to engineer different products. In food science, the speed of solubility changes the experience of eating a particular food. It may change the flavor and make the food more interesting to eat. In pharmaceutical science, it makes it possible for you to take a medicine in the morning and have the medicine continuously help you all day long. In our experiments, we are going to explore solubility and the speed at which chemicals dissolve so that you can design and build a time-released medication tablet. For our first experiment, we are going to test how different solvents affect one solute.
Okay, so you're going to need 3 solvents, cups, and 3 pieces of candy of the same color. The solvents are oil, alcohol, and water.
The first thing you are going to do is to pour 5 milliliters of liquid into each of your measuring cups. Use the measurements on the side of your cup so that you get the right amount in each one. Make sure you know which liquid is in which cup. Once your cups are filled with your liquids, place a candy in each one. Swirl each cup around for about 20 seconds, and then watch to see what happens to the candy in each cup. In Table 1 of your journal, write down what you observed in each liquid. When you look at the candy, how much of the colored candy coating is gone? What colors do you see in the liquid? How much of the color is in the liquid from the candy coating? Then observe how the candy dissolved in each liquid and label each one as best, medium, or worst solubility. Remember, the best solubility is the candy that dissolved the most. All right, now that you've watched us walk through this experiment, it's time for you to try it out yourself. Pause the video now so that you can test out solubility of candy in different liquids too. We've tested out what happens to our candy in different liquids, but now let's observe the patterns of solubility in water. What happens when we put our candies in water? What patterns do they make as they dissolve? Fill a plate with water and place 3 different colored candies in the center of the plate. Watch the candies for about 1 to 2 minutes without touching or moving them. What did you see? Record your observations in Table 2. Pause the video now to test out solubility patterns yourself. You can follow the procedure on the screen for your experiment. Nice work with that last experiment. We just finished testing how different solvents affect solubility. So now let's see what happens when we change the form of our solute. Here's what you'll need for this experiment.
Hi campers, we have the antacids, we have the pH paper and the pH paper scale, the vitamin C, and we have a spoon, water, 5 cups, scissors, a ruler, and a pencil.
The first thing you need to do for this experiment is to cut your pH paper into 1 centimeter pieces. Use your ruler to measure your pH paper and make a mark with your pencil for every centimeter. Then, use your scissors to cut on the pencil lines you just made. In the end, you should have 25 pieces. Next, take your large plastic cup and fill it with water. Make sure that you leave some space at the top so that when you stir your solvent, it doesn't spill over the edge. Then, here's what you'll do next.
We're going to make our solution by putting the vitamin C in the water and stirring.
Once the vitamin C powder has completely dissolved in the water, you will want to test the pH of your new solution.
Test your pH by dipping the pH paper into the solution and then comparing it to the pH scale.
Once you've matched the color of your paper to a color on the scale, record the pH on Table 3. This is your initial pH of your vitamin C solution. Next, set up your 5 medicine cups in a row on a piece of paper. Place 1 tablet in front of each cup and label the paper with that tablet type. You will see that you have 4 different types of tablets: 2 pressed tablets, 1 chewable tablet, 1 soft tablet, and 1 candy-coated tablet. We have a labeled picture on the slide to help you identify which one is which. The soft tablet will need to be unwrapped and should be labeled soft on your paper. The chewable tablet should be labeled chewable, and the candy-coated tablet should be labeled coated. Then, take one of your pressed tablets and label it pressed. Take the second pressed tablet, put it in a baggie, and stomp on it with your feet like you can see us doing in this video. It doesn't have to be perfect, but it needs to be in pieces when you finish. Once you finish doing this, you're going to label the paper powder. Finally, you're going to pour 15 milliliters of your vitamin C solution into each of your medicine cups. Use the measurements on the side of the cup to help make sure each one is equal. Once you've done this, you're all set up to start the experiment. You can pause the video now to follow our setup procedure for this experiment. Great work getting set up for this experiment. Now we're going to test out our antacid forms. We will be testing each tablet, one at a time, for 4 minutes each. So make sure you have your timer ready. First thing we're going to do is put 1 tablet into its cup and start a timer for 1 minute. After 1 minute, you're going to gently stir the cup with your spoon and dip a new piece of pH paper in the cup for 1 second. Compare the paper color to your pH scale and record this pH in the 1 minute column of Table 3 for that tablet. Wait 1 more minute and stir the cup again. Dip a new piece of pH paper in the cup for 1 second and compare the paper color to your pH scale. Record this pH in the 2 minute column of Table 3. Wait 1 more minute and stir the cup again. Dip a new piece of pH paper in the cup for 1 second and compare the paper color to your pH scale. Record this pH in the 3 minute column for Table 3. Wait 1 more minute and stir the cup again. Dip a new piece of pH paper in the cup for 1 second and compare the paper color to your pH scale. Record this pH in the 4 minute column of Table 3. You're going to repeat this process for all 5 antacid forms. Once you've recorded all of your pHs in Table 3, you're going to want to graph your results. Here's an example of how to graph your data. Feel free to use a different color for each type of tablet so you can better see your results in the end. Remember, your numbers are going to look different than mine. So let's say I just finished testing my pressed tablet. The first thing I want to do is make sure that I mark our initial pH of the vitamin C solution. So at 0 minutes, because we didn't start our experiment yet, we're going to go to the 0 at the bottom and up to the 4 because that's what I recorded as my initial pH. When I tested my pH at 1 minute, I got a pH of 5. So I'm going to look at the bottom and go over to the 1 and then up to the 5 on the left-hand side and mark a dot where those two meet. I'm going to do the same thing for 2 minutes. So I also got a 5 pH at 2 minutes. At 3 minutes, I got a 6 pH. So along the bottom, I'm going to go over to the 3 and move up to the 6 and mark a dot there. For 4 minutes, I got a 7. So I'll mark a dot at 7 for those 4 minutes. Once I have all of my dots on the graph, I'm going to draw a line connecting them all so I can see the trend throughout the experiment. Once you've graphed the data for all of the different tablets you tested, compare your results. Which form worked the fastest to change the pH? Which form worked the slowest to change the pH? Write it down in your journal. Now that you've watched us test out different antacid forms, it's your turn. Pause the video now to follow our procedure for this experiment. Nice work! So far you have tested how changing a solvent affects a solute and how the form of a solute affects solubility. Now it's time to put together everything you've learned for our final experiment. Your final challenge is to design a time-release medication tablet. In this design challenge, you need to deliver 2 medicines in 1 pill. We are representing these medicines in 2 color tablets. You have to use these 2 different color tablets in your pill, and the final tablet has to be 1 single unit and needs to be fully enclosed, so both of your 2 different color tablets need to be together. And then when submerged in water, your tablet has to release each of the colors at a different time. The first color needs to be released after 30 seconds, and the second color needs to be released after 3 minutes. Before we get started, here are the materials you'll need for this experiment.
You'll have 3 different kinds of plastic, a spoon, water, 4 different colored tablets, tape, and scissors.
As you discovered throughout our other experiments today, every solute is a little bit different. So before you design your time-release medication tablet, make sure you know what each of your materials does in water. Test out a small piece of each of your plastics and observe. What do you see happening? What happens to a small piece of Scotch tape? Make sure to document your observations on your design plan. Don't forget to also test out a tablet. As we know, solutes dissolve differently in different forms. So decide how you want to test your tablet, whether it be whole or in powder form. Observe what happens and write it in your design plan too. Once you've observed what happens to each of your materials in water, it's time to start designing. Remember, scientists always write down their design choices so that they can remember their alterations and change as they experiment. Use your design plan to brainstorm some design ideas for your time-release medication tablet. Draw a diagram of what your design will look like and label what materials you will use. When your design is done, it's time to create. The final step is to test out your time-release medication tablet. Take your newly designed tablet, drop it in a cup of water, and observe. Did it work? Remember, even if it didn't turn out the way you expected, you still learned a lot today. It's all part of the scientific process. Thank you for joining us for today's investigation and engineering challenge. I know we had a lot of fun, and I hope you did too. STEMKits are a product of iBio, delivering industry-led STEM programs for teachers and students to inspire a new generation of innovators and entrepreneurs. To learn more about iBio and its programs, visit www.ibio.org.